Hello. Here we continue examining continued fractions. And the examples which we will work out through will be of quadratic irrationalities. So the first, square root of 5. The building of the continued fraction is iterating the same procedure. First extracting the integer part, and the integer part of the square root of 5 is 2, because the square root of 5 is in between 2 and 3. And then writing the fractional part as 1 over something. So the fractional part is square root of 5 minus 2, and then we have to flip it to put it under 1. And now this is a number which is larger than 1, and we continue. So to continue, we have to take this number and rewrite it first in a better form so that we can see what is its integer part. And beta would be just clearing the irrationality in the denominator, so multiplying by the algebraic conjugate, or up to a sign. This is the algebraic conjugate. So the denominator becomes a difference of squares, 5 and 4, and that is 1, and so we have square root of 5 plus 2. And square root of 5 is in between 2 and 3, and this number will be in between 4 and 5, because it's just a shift by 2 of the square root of 5. And so the integer part of that denominator is 4, and then we continue writing the fractional part of this number, which is square root of 5 minus 2, as 1 over. So it is 1 over 1 over square root of 5 minus 2. Square root of 5 minus 2 is the fractional part. And again, 1 over square root of 5 minus 2 has to be analyzed for the integer part and the fractional part and so on. But we already did it, so that's what we did here. We extracted the integer part, which was 4, and then the fractional part was square root of 5 minus 2, and yes, we are going to repeat. We're going to repeat extracting the same integer parts forever. And in the continued fraction notation in abbreviated form, we will have a sequence of integer parts which will be just 4. So the shortcut for that is just the write one period, full period, and underline it. The period is just one number 4, it just keeps repeating. So that is a very convenient form of writing the square root of 5. That is a very compact information which describes it precisely. And this can also be used to find very good approximations for this irrational number. Approximations by irrational numbers by computing what are called convergence of this infinite continued fraction, and they are rational numbers which are just truncated versions of this infinite continued fraction. So let's see what are the first few. 2 is just 2. 2 over 4 is by the definition 1 plus 1 over 4, which we can write as 9 over 4. 2 and 2/4 will be 2 plus 1 over 4 plus 1 over 4. And the first step is to simplify this. And that will be 16 over 4 and 1 over 4, 17 over 4. So that is the same as 1 plus 4 over 17. We're getting more precise with our approximations. Before we had 1 over 4, which is 4 over 16, and now we have 4 over 17. So a tiny, already minuscule decrease in the number. But let's just write it as a rational numerator over denominator, so that will be 34 and 4, 38. I could start plotting the approximation if this is 2 and say this is 2 and a quarter, so 9 over 4. Then this number will be below it, but very close already, so I'll put it not up to scale. This determines the scale as 1/4, but that will be slightly larger than 1/4, the distance between 38, 17 and 9 over 4. So I know that my square root of 5 is somewhere in between. It is always in between two neighboring convergence. And you could see that odd convergence involving odd number of components are below the approximant, the actual number, and even convergence are above. So square root of 5 is somewhere here. Let's compute one more convergent, and that is going to be 2 plus 1 over 4 plus 1 over 4 plus 1 over 4. So we have computed this bit. That was 4 over 17. And so to move, we have to combine that into one rational, and that will be 68 plus 4, so it will be 72 over 17. Then we flip it, 17 over 72, and then we combine it into 1, so over 72. Twice that will be 144, and with 17 on top it will be 161. So that is going to be just after my square root by getting increasingly closer to it. So 161 over 72 is the next convergent. And you could see that you really approximate numbers very quickly. That was, before calculators, was a practical way of approximating the rational numbers, dealing with them in, say, engineering applications. Well, let's do one more example, another square root of 3. And that starts the same way, so we extract the integer part, always the same way. And the square root of 3 can be put between 1 and 2, so the integer part is 1. And again, we take the fractional part, which is going to be square root of 3 minus 1, and we flip it. We invert it and put it under 1, and that number becomes larger than 1. So the iteration is, starting with this number, extract its integer part. But first let's make it prettier by multiplying by the minus algebraic conjugate. So the denominator becomes 3 minus 1, and that is square root of 3 plus 1 over 2. So the square root of 3 is in between 1 and 2, and that number will be in between 1 plus 1 over 2. I just replace square root of 3 by its bound 1, and here I will replace by its upper bound 2. That is just an integer 1, that is less than 2. So again, the integer part of this number is 1. And then the fractional part is, I have to take 1 out, and that will be square root of 3 minus 1 all halved. So when I flip it, I'll have 2 over square root of 3 minus 1. So my next step is to take this number and again rewrite it in a better form, and that involves again multiplying by its conjugate up to sign. Here I have the product with the conjugate, which is just 2, so 2 cancels out and I am left with square root of 3 plus 1. And that is bounded from below by 2 and from above by 1, so my integer part becomes 2. Sorry, from above by 3, my integer part becomes 2. And then when I compute the fractional part, it will be this without 2, so that will be this number. And we hit the repetition, so here I'll have to write it as 1 over 1 over 1 square root of 3 minus 1. So that is already computed, and the fractional parts go like 1 and then 2, 1 and then 2. So writing the result as an infinite but repeating continuous fraction, I'll have 1 and 2, 1 and 2, and so on. So this time the period is 1 and 2. The abbreviated form will be there. That's it for these examples. See you later.